Okay, shall we get started? Right, so my name is Carsten Rother. I'm, as Andrew Blake, from Microsoft Research Cambridge. So I will give 2 lectures, and so this is 1.5 hours, and there's another 1.5 hour lecture. So I will follow up on quite a lot of the topics Andrew Blake already kind of very briefly mentioned. So my talk will be mainly about discrete models, optimization, and a lot of different applications. So if you have any questions during the talk, I mean, there will be some things which are quite fast. I mean, I don't expect you to understand all of the details, but if you have some fundamental questions or general questions, just like ask, interrupt me. We've got enough time. Okay, so the outline for the 2 lectures will be, I start with an introduction on random fields. Then there is a lot about models used in computer vision. I go through a lot of the models recently, and in the last 5-8 years have been done computer vision using discrete models. Then there's basically, I will start hopefully a bit of optimization techniques, and I will stop here. And the second part of the lecture is optimization, comparison, and I think I should have time for another advanced section where I will actually talk about some improvements on recent Kinect work we've done. Okay, introduction to random fields. So throughout the talk I will use the following notation. So Z is an image given here, so it's RGB, 3 color channels, n pixels. So in this case, I don't know, like 6448 could be the size here. The user has, for instance, indicated, gives scribbles here, which is black, blue is for background, and red is for foreground. And the goal is to determine for every pixel n a binary label, if it's 0 for background or 1 for foreground. So this is one of the most simple or standard problems computer vision, and I will use that kind of like toy application, or that application, quite a lot to demonstrate some of the aspects. Okay, so let's write down the probability here. So Z is given, X is unknown, so we can write down the posterior, which means given Z, what is the probability of the labeling X? So it's known as the posterior, which is decomposed into a likelihood and a prior. So a prior only works on the unknown labeling X, and the likelihood says if I were to know X, how likely is it that I really observed Z? And I will explain all of this here with some graphics in a second, how we can build it for this very simple application here, how we can build likelihood and prior. Then there's another thing to make this a proper distribution. You need a called partition function P of Z, but very often people assume this is constant because it's like, what's the probability of observing an image? It's like every image is kind of like a possible, I mean, every image we get in is a possible image. So this one can be seen as constant, and then we get, we can say this is equal up to just the likelihood and the prior. So then most parts of my 2 lectures will be about a maximum a posteriori or a map estimation. So the goal is, you say, for every segmentation X, you can evaluate the posterior, and you just say what is the optimal labeling X star, which maximizes that posterior. So this is the called maximum a posteriori or map solution. Okay, and in the beginning of the talk, I will then transform this problem here into a problem called energy minimization. So we simply say, we again go over all possible X's, and we look at an energy, and we simply minimize that energy. And I will make that conversion of how to come from a probability maximization to an energy minimization. It's very straightforward to do. Okay, let's look at this example here. The user has given us some brush strokes. We could, for instance, so these blue ones are the dots here, and the crosses, it's a bit hard to see, the crosses are for foreground brushes. This is a slice through red and green. Now we could fix like a Gaussian mixture model. The blue is here for the foreground, and the red is for the background. So these, I think, are, I don't know, probably 8 Gaussians or 10. So we could fit a Gaussian mixture model here. And with that Gaussian mixture model, you can exactly say, well, if I observe a certain color, it's say, I don't know, yellow, is it more likely to be foreground or background? So obviously the red and the purple colors here are more for the foreground, and the dark ones are more for the background. So if we now say, let's look at the likelihood, if we say, assume I know its background, I look at this Gaussian mixture model, and for every pixel I see how close it to that Gaussian mixture model, right? I see that the dark colors are more likely, so bright is a higher probability, are more likely background, and dark colors are more likely foreground. So yeah, the other way around. So dark colors are not background. And here you can evaluate foreground. We fitted this Gaussian mixture model, and then we see already a bit of the starfish shape appearing. So that's quite straightforward. And now we can say, okay, let's look every pixel independently, and that's called the maximum likelihood estimation. Every pixel, if we were to have this probability where this posterior, where we just have a product over all of the individual likelihoods, we can then estimate the maximum likelihood by taking every pixel the optimal selection, and this gives you this image here where you still see some holes in. Okay, so how do we overcome these holes? We introduce a prior, and the prior tries to encode something about the labeling. And this is the most simple prior, and we will look at a lot of different priors throughout this, these two lectures. So if you look at two neighboring pixels, xi and xj, then it's more likely that they have got the same label compared to having a different label. So if you look at the starfish, there are a lot of neighboring pixels here. They're both 0, they're both 1, 1, or they're 0, 0. There are some which straddle the boundary, which some goes from 1 to 0. But they are less likely. So we encode that as in this called like Ising prior. There's an exponential minus and the difference of these two pixels. So the bottom line is if they are the same, 0, 0, 1, 1, you get a 0 here. So exponential 0 is 1. Or if they're different, 0, 1 or 1, 0, it's a 1 here, so it's exponential minus 1, which is 0.36. That means that the probability of having the same label is higher than having a different label. Okay? You will see in a second why we have done this bit weird thing with exponential, but bottom line is simply you have two labels here, two labels here. You can have all these 4 combinations. There are only 2 possible outcomes, and one is more likely than the other one. Okay? Now if you look at this, we could just write down this prior. This is a proper distribution here with some partition function again. This is simply the product over all of the possible pairwise terms for all of the neighboring terms here. So this goes for all of the 4 connected, let's say 4 connected grid in an image. So all of these pixels are, each pixel has got 4 possible neighbors, and they're all connected with these terms here. And this is a fair sample from such a distribution here. So that means you see here that they're quite often the same. They're 1, 1 or 0, 0, but there are still some of the pixels are also 0 and 1. So there's some transition with the labeling. But observe that, like, obviously the optimal labeling is everything black or everything white, because this is like if you maximize this distribution here, then everything 0, everything 1 gives you the optimal value for this here. So this is the optimal peak, and we will actually come to that later on. We will see that there are some problems with it, but we also see that we need some likelihood. Otherwise, with a pure prior, we get these trivial solutions. Okay, so now we can put all together. This is then the Gibbs energy. So we write it down in this following form using an energy. And I will come to then in a second to energy minimization, but you will see in a second why I write an energy here. So the energy is composed of these terms here, which are unary terms, which come from the likelihood. And this means here, if we sum over these unary terms, they're just minus log probability of being foreground, and then you multiply it with xi's. So if this one here, if xi is 1, then this one here is active, the foreground. And if xi is 0, then this one here is active. Okay, so we've got some term here which represents our likelihood, and that's called the unary term. And we've got some term here which represent our pairwise term. And now you see there is an exponential minus of this thing here, so that's exactly the Ising prior which we had before. So it's exponential minus and this thing here, which is our Ising prior. So okay, now we have this so-called Gibbs energy, And actually, yeah, so this is the distribution here with some partition function. And now let's see that we can convert, taking the maximum of that called Gibbs distribution is the same as minimizing this energy. We will see that now. So we convert, we can take the minus log of that probability, and if you just take the minus log of this whole thing here, it's minus log of this function here, plus, and the minus log of this log of, and x cancel out, so minus is a plus, we just get this here. Now since this partition function is independent of x, which we normally maximize over, so basically taking the maximum of that posterior is the same as taking the minimum of that energy, because the minus turns the max to a min, and the log doesn't change anything about being a minimum. So this really says that maximizing this posterior is the same as minimizing the energy, and we can just talk about energy minimization. So we've got an energy here, we have an x, and we minimize over that, that's an x star. And this is the underlying energy. And now we see here, if we put the two things together, we've got that was the maximum likelihood. This here is switching on the prior and combining it in some way, and I will talk about this W in a second. We get a much nicer result. It's cleaned up. So most of the pixels are both 0, 0 or 1, 1, the neighboring ones, and it's also following a bit the likelihood, what the likelihood has told us. So now you could ask, well, what about the W? If the W is, for instance, 0, we go back to the maximum likelihood. If W increases, then we get results which are more coherent. So what would be the result if W goes to infinity? Sorry? Will be? To the trivial solution, exactly, yes. And actually, I think if you go more to the limits, it actually starts to be a bit more a circle, because this is the minimum boundary length you can have. Like if this one has a longer boundary length, you cross more of these 0, 1 terms, and the more you increase it, it might get towards more like circular shape, and then it will disappear. Okay. So one trivial way, and I will come to much more sophisticated in a second, one trivial way is to say, well, how could you choose this W? And one very trivial way is to say, well, I've got some training data, which I've got here images, I've got trimaps, and so the trimaps say inside is definitely foreground, outside is definitely background, the gray area I have to get some segmentation, and there might be some ground truth labeling with it. Let's say we just pick a certain W, and then we evaluate, then we run our technique, we get some results, and now we compare in terms of pixels how many have been classified correctly, or how many are correct, how many are incorrect. And that's called, so measuring that is called a loss function, and the number of misclassified pixels is called the Hamming loss. So basically we try to optimize W under the Hamming loss. And so we could look at different W's, and we can look at this error, and you see that it goes down, and a certain W is a good value, and then when you have a larger W, it starts to increase. Okay? So actually in an exercise you will have a chance to play around with some of these settings and actually re-implement some parts of these. Okay, MRS-CRF models in vision. So this is a very general overview. So we have different models. They can be discrete or continuous variables. They can be discrete or continuous space. There is dependencies between the variables we have to talk about. Mainly in this talk I will talk about discrete variables and discrete space, and mainly about dependencies of these variables. But in the end, of the introduction, I also come to continuous variables and continuous space. Then there are a lot of applications. I will go through quite a lot of them, how they are done with discrete models. Then the main part of the talk is about, or tomorrow's lecture is about optimization techniques. So finding this map solution, and there is a large list of techniques, and I will go through quite a lot of them. And then there's learning, like how to learn, for instance, this W parameter. And I will actually now do a detour on learning, because I think it's quite important and relevant. So let's do this now. And Christoph Lampert will talk in, I think, in 2 or 3 days' time. And he will go through a lot of these concepts again and explains them in a proper way with equations. But here I already put some of the foundations of this learning. So we actually, I mean, you've seen we introduced it with this probability, but in the end it came down to energy minimization. So you could wonder why did we talk at all about probability, right? We could just say, oh, there is an energy, let's minimize it. And Andrew said that was one of the key contributions like 15 or 20 years back, when people start to at least write down proper models and optimize it. And I think now is the time where a lot of machine learning people come in, where they say, well, okay, what you think about learning as well, right? Not only just optimization. So let's talk a bit about learning. So also it just started like a year ago to look in more detail in it, but I think it's quite fascinating. Okay, so for a second, let's assume we have a distribution P of x given z, comma w, and w is the parameter which we want to learn, right? Which we have some training data, as I said before, with the frog, and we want to learn this w, and it can be many more parameters, not only this particular w, it could be a large number of parameters, and I will, in the second half of the talk, I will talk about models where I've got 1.5 million parameters. Okay, so let's assume we were to have such a distribution which fits our training data, and I will come in 5 minutes to how do we actually learn this, but let's assume we have that. And let's talk about a bit decision theory about what to do when you have the distribution, what actually X star solution you should take when you have that distribution. Okay, so what it boils down to is what we want to minimize. We want to choose an X star which minimizes our expected loss. So the expected loss is written with this equation here. So that means that the expected loss is the following. If we have X star as our final solution, is one solution we pick, we look at all possible other X's and look how different they are. This is called the loss function. And then we weight it with the probability of that certain solution. Okay? And we sum of all of these possible X's. And this is called the expected loss. And so the idea is really to choose, that's most general, and you will see that it makes a lot of sense to choose an X star which minimizes this risk. The main question is, what do we choose as loss function? And now we'll see in a second that different ways of making that decision really depends on what loss function to choose. Okay, so I've got a question now to you. So let's assume we have this distribution P of x given z, comma w, and I've made that up. I actually wanted to do that properly with data, but I didn't have the time to do it. So assume here the segmentation task is the following. Actually, the image, let's turn it into gray, which makes it much more ambiguous. So the universe might be much more ambiguous, and there are these brush strokes. Let's just assume that we have X here is the space of all possible labelings. Okay, so each possible labeling of the outcome has a space here and has a certain posterior. Okay, and assume this is fixed here. And now let's say, okay, these ones for here are instances. They are have a bit higher posterior, and this one here actually happens to be a higher posterior than these ones here, but it happened to be like a pretty bad solution. So this could happen if the universe are quite ambiguous. Then we actually, this one here is a not bad segmentation because it's very compact. So the transitions of 0 to 1 are far less compared to this solution here. Okay. So what if you have such a distribution here and you see this here? What output X star would you choose? Pardon? Depends on the loss function. Yes. Yes. So, but yeah. So intuitively, one say, well, it would be nice to choose one solution here, right? And now we see what happens. So if we use the following loss function, which is called the image-wide 0-1 loss. That really says, the loss function says here, it's zero loss if the X star which I choose is equal to X and 1 otherwise. So it's like a constant, otherwise a constant loss. So if you plug this in here, what we see is everybody pays a 1 apart from the right solution X star which we choose. That means to minimize the risk, you have to choose the solution which is the most likely one, right? So under this loss, it only cares about one solution, which is the right one, and the best one to pick is the one which is the most likely. So if we have map, in this case, you would choose this solution here, right? Which is the map solution in this case. I mean, it could happen that this peak is slightly higher, and then you would choose a sensible one, but in this case, you would choose this solution. So I made it a bit more extreme, and the second comes actually a real application. You could choose a different loss. You could say, well, what I really want actually is the Hamming loss. That means you choose, if you were to, with the Hamming loss, it might be that, or quite likely with this setup example, it might be this one here, the best X star. That means you take the right X star, compare it to all possible other X's, see how similar they are in terms of pixel difference, okay? And then you weight it with how likely they are. And see, there's a lot of mass in here, right? And therefore, it's quite likely you would choose this solution here because of all the mass here of these other solutions, which are very similar in terms of segmentation and very high probability. You would choose much more sensible solution here. So this is called maximum marginals, and so what you maximize here, actually you compute the marginals, which I'll come to in a second, and then you maximize for every pixel, you take the maximum marginal. So here's now a real world example, which is taken from the recent book of Sebastian Novotny and Christoph Lampert. So first of all, the marginal is really, the marginal is that you pick for a certain pixel, you say if it were to be labeled 1, you sum over all possible other configurations where you only fix that particular labeling as 1, for instance, and you sum over all possible other labelings. So that's called the marginal. And so this is quite interesting here. So first of all, this here is, if you fix it to 0 and 1, it's kind of a distribution, so it's the posterior marginal distribution, and this is what we see here. If we fix every pixel here to 0, what is the probability? And then we see that these are the marginals, and if we take for every pixel, you can also compute the one for 1. If we take for every pixel, is it more likely 1 or 0, you get this solution here. And you see here that the task was to detect the buildings, or it's a building detector done by blocks, and you see here the solution is better than if you take the map solution. So the map solution would be this one here, where actually this one here is taken out. So this would be not part of the building. So you see, by taking different loss function, you actually get a different result in the end. Okay? Now there's something else you could say is the pixel square loss, which is if we don't have to have, we don't necessarily have binary labels, we could have multiple labels, and then it's just the difference, the square difference about these two observations, x and x star, and we get something called the MMSE estimate, minimum mean squared error, and it's actually weighting with the marginals all of the solutions, and you sum over that. Okay, so now I haven't talked about how do you get the probability, and this is a very standard pipeline, and Christoph will go into quite length into detail about this pipeline and how exactly to optimize this distribution P here. So typically what you do is you have some training data, xn is some training ground truth labeling, then the images, and then you have a maximum likelihood estimation where you really try to use, you have a product of all possible training examples, and then you maximize your posterior with respect to the W, and you might have some regularization on W as well. Okay, and so you maximize over W, and Christoph will go, I think, into quite length how to do these things. There are a lot of, it's a big problem how to do it with loopy graphs and so on. My main point was to say, if you've done this here, it really depends on the loss function, what then method you should choose in order to get out your best X star. So it's a two-step procedure. You first try to do maximum likelihood estimation, and then you get your decision out. So we've done that in a recent paper, for instance, on a quite very simple graph. So that's for denoising. So you have some training images. There is some noise on. I hope you can see that there might be some bit of speckle noise on. It's pixel independent noise, and these are ground truth, which with no noise. And then we use this maximum called actually pseudo likelihood learning for a 4 connected grid. And I will come in a second how the potential exactly look like. So now you've got some test image and some, so this is the true test image. There's some noise and you might only see it on the horse here, and they're zoomed in, so these are the end result. So this is really the map solution, and this is the MMSE solution. And you see, oh right, this is, this here, actually I can hardly see it, but I think you see that this one here looks better than this one, right? In terms of results. So this one here is kind of very blocky. There are like big errors with the same labeling. So this one is visually much better. Do you see that, or yes or no? Yes. Yeah. Okay. Good. So then you say, oh, okay, map is then not interesting, right? Because this is a much nicer solution. I should always do minimum mean squared error. Okay. But there is an alternative pipeline, which is now quite interesting, which also Christoph will talk in detail about, which says, well, we could take all the training data and now so this is the standard pipeline I just explained. So we have a two-step procedure, but there is this alternative pipeline called loss minimizing parameter learning, and it's just a one-step procedure. You have, let's assume during test time, we say we want to use map during test time, okay? Now we've got the trained data with the ground truth labeling and the images. Now we just run this one optimization where we say, well, give me the best parameters W so that they minimize the risk and so that they minimize the risk using map estimation. So you simply say, give me the best W, and you could also regularize the W's, put some regularization on, which minimizes the risk. And so now we know, we basically plug in the knowledge of the loss function directly into the learning, because we say under this loss function, under the loss function here, minimize directly the parameters. Okay, so Christoph will go into detail how this is done, but it's kind of interesting. So now we do exactly the same family of models, and we've learned the parameters differently, and I'll show you in a second what the parameters are. But here are the results. So if you use map now, suddenly it looks much nicer and far less blocky as we've seen before. And obviously, if we now plug in the pixel squared loss, so if we plug in MMSE, it doesn't make much sense because we really optimize it with map in mind. So it's actually quite interesting. We can compare now the different models which are learned. So I will use similar figures later in the talk, so we can explain them now in a bit more detail. So this is the unary potential, which simply says that we have an observation Zi, which is a certain color or gray value for that pixel. What is it different to the labeling we really obtain then in the end? And if they're the same, we pay minimum energy, and the more they deviate, the higher energy we pay. And so you see now it's quite interesting that the functions which are learned with the probabilistic engine and the loss minimizing are quite different, right, in terms of structure. And so it's no surprise if you use map for this one or for this one, they will produce different results. And this one was really designed to work best under map, right? So the pairwise potentials here are the difference of the two neighboring pixels of the final labeling. So what is preferred is that they have the same labeling, but if they have different labeling, they start to pay a higher and higher penalty. But again, it's interesting that these kind of functions are slightly different when you learn them. And so we can do a side-by-side comparison. Actually, we see that, and even we confirm that with numbers, that actually the loss minimizing and map gives better results than the probabilistic MMSE approach. Slightly better. Visually, I think slightly better. If you look here, for instance, at the graphs here, there are more details up here visible, which is also in the true image than down here. And actually, and I think there are some more studies in machine learning, you can show that if the probability distribution is not really fitting the data well, and that we nearly always have in computer vision. I mean, our model never fits perfectly the data. Then it's actually better to use this loss minimizing and map scheme compared to the standard probabilistic pipeline. So actually we've done some synthetic experiment where we looked at this, where we kind of like deliberately constructed a model which deviates from the true model, and the more it deviates, the error is much higher for the probabilistic approach compared to the loss minimizing approach. So let's summarize. So map estimation is important. Either sometimes you have systems where there are just a few parameters and we can handcraft them or like choose them in some intuitive way. And a lot of vision systems are built like that, right? And where we don't use any proper learning and so on. They're just like handcrafted. And then map is obviously very important. Or optimization in general. We could use, as I just said, loss minimizing parameter learning or cross validation. Actually, just as a side comment, actually when you do that, and Christoph will talk about that, map estimation is very important as part of the routine. You actually typically a routine for optimizing the parameters or finding the parameters is actually a constraint generation where each constraint is solving a map estimation. And it's actually very important that you get global optimality of it. If you don't get global optimality, you get into quite a lot of trouble during learning. And so therefore quite a lot of the talk will be about global optimality or getting good solutions. And this is, so therefore it's quite important actually for this part of the learning. Also one has to say that uncertainty or probabilities later on, as well as like marginals, are important if it's part of a bigger system. If you want to have your model system built into a bigger system, it's good to have uncertainty. As a side comment, there is actually a map-based uncertainty as well, which is called the min marginals, where instead of before I had a sum here for computing the marginals, I could replace it with a max. And then you can actually also use efficient map solvers to get out these called min marginals. Okay, that's kind of the stop of my learning section. Are there any questions on this? It was quite clear, or? Yeah?
Could we use any other loss function minimization for the second part pipeline?
Yeah. Actually, I've done that. For instance, I've done. It can get more tricky with different loss functions. But one thing I've done, for instance, was to say for interactive segmentation, what I really care about is how many brushstrokes, how many user interactions do I need in order to get the ground truth, right? So I minimize the number of user interactions. And we've done actually a max, this loss minimizing pipeline with that objective function in mind. It's got actually quite tricky because of exactly that issue that you don't get the map solution during a step. But that's exactly what I think one has to do. So one has to really think about what is the right loss function, what do I really want to optimize in the end, and yeah. Okay, let me just get a drink. Okay, so let's go back to the main part. So we had this overview here with models, application, inference, and optimization and learning. So I very briefly introduce what's very useful when you describe energies or probability distribution. They're called vector graphs. So graphical models are very popular tool in machine learning. There are various forms of how to write graphical models. There are undirected graphical model, directed graphical models, undirected graphical models, and vector graphs. And for quite a lot of the vision problems, when you really deal with, in the end, with energies, vector graphs are the most useful way of visualizing energies. And I will explain one example in a second why that is. Okay, so vector graph is something very simple. So let's assume we have this Gibbs distribution here with these ones. This is energy with a vector here or like a function here, which depends on 3 variables, 1 and 2 variables here, 2 variables here, 2 variables here. So we visualize it in the following way. We simply use for every variable here, we use an empty circle and put the labeling, put the variables in here, x1 to x5. Now we simply connect all of the variables which are in one vector or in one function here. We connect up and have a square here, and that's like, yeah, that's so from this visualization here, you can very quickly see what is at least the structure of this energy. You don't know exactly the form of the factors, but you see very easily, just visualize the structure of it. You see here, there is so-called, I will come to that in a second, called triple clique, or a factor with 3 variables, arity 3 and 2 here. So again, here's the same. So what I will define as the order of a function in general of this energy, the order is the arity, or the number of variables of the largest factor. So this energy has order 3 because there's one factor with 3 variables in here. So I will use actually factors and clique in the same way. I will not distinguish, and that's not fully correct. That's just as a side comment, like for instance undirected graphical models. This is the undirected graphical model to this one here, to this factor graph. And one thing which is ambiguous with these undirected graphical models is how they exactly decompose into factors. So in an undirected graphical model, everything which is fully connected, like this here, this triangle here, and this here, this is fully connected, they form a so-called clique. But the clique could either be a true factor with 3 variables, or it could decompose into pairwise. And this is ambiguous if you write it as an undirected graph. So therefore, the factor graph exactly tells you how the energy looks like. So the definition of the order, I use same for clique and factors. So random field or Markov random field, so the Markov property, and that was Andrew Blake already hinted towards, is that the random field has low order factors. That it really isn't largely connected. There are not many higher order factors which connected to a lot of variables. We have most of the time pairwise or triple clique some low order factors, and that's called the Markov property. The local dependency, it's a local dependency, but you still have a kind of what Andrew called the knock-on effect. So this variable is still can influence via the factors this variable down here, but it's only low connectivity and not everything is connected. It's not one big factor. Okay, so some examples of factor graphs, and I will go through a lot of applications using these different factor graphs. So this is 4 connected with order 2, so-called pairwise energy. We've got just these factors here as 4 connected. We can have highly connected. This is an 8 connected, where a central pixel is connected with 8 neighbors. And then this is a higher order random field, where there is like one factor here which connects to all of the variables. Okay. Now let's look at some of the examples used in computer vision. We've seen already segmentation. So we now write it, visualize actually slightly different. Also Andrew has done that already with observed variables with shaded circles. So these are observed variables, and these are unobserved variables. And yeah, so there are some unary factors, which are these ones here, which just connect to observed variables. And these are pairwise factors, which connect to unobserved variables. And that was the image segmentation example as a factor graph. Something which is very useful and called conditional random fields is, so conditional random field comes a bit more from discriminative models, but one thing what conditional random fields can do is like that all the factors can depend on the observation on the input image. And here, for instance, we have got one where the pairwise factor depends on the image observation, which is something very useful. And for a lot of applications, nearly all of the application computer vision with discrete models, the pairwise or high order factors depend on the data. So here this function has the following form. If the 2 neighboring pixels have the same color, I have a higher penalty. If they have a different color, they have a lower energy. And the reason is that this could be more likely in edge here, and this is less likely in edge for segmentation. So you see here that this is the result with a Markov random field where there's no conditioning of the pairwise terms. So this is a pure Ising prior, and I think hopefully you see a bit of black here. And this one here is a much better outline. Here follows exactly the boundaries here of the segmentation, and this one is a contrast, so-called contrast sensitive term, and the data enters here. So this is the underlying factor graph, but it's not overly exciting. Okay, let's look for instance at stereo. So in stereo we can start, and I come to more sophisticated stereo methods, we could start with 4 connected grid. So we simply have unary potentials, or coming from likelihood, and I will explain that in a second. And then we've got pairwise potentials, and I will explain that. So here for stereo, most of the time you assume that the images are rectified. That means that a scan line here corresponds exactly to a scan line here. That means to find the corresponding point here, you have to take one particular point, I don't know, let's take the tip on here, on the head, and find exactly on the same scan line, you have to find the corresponding one. If it's at infinity, like as far away as possible, then it's like the shift towards the left is 0. So it's exactly the same position here on the vertical. And if it's the closer it is to the camera, the more it's shifted to the left. And so these are called disparities or depth. So the goal is to find the optimal, so we express this here as a multi-label energy with, where D has got from 0 to capital D possible values, and every pixel has got one of these values. Now we have to define an energy which exactly encodes that good solutions have got a low energy and bad solutions have got high energy. Okay, so let's look at the unary term. The unary term can, for instance, be done by sum of square difference in the following sense. You take your current pixel, you shift it by the disparity which you think it could be. So that's your unary term. You know what disparity you might expect. So you've got that's a unary term, looks at the possible labeling of that particular pixel, and then you shift it by that amount, and then you look at what is the underlying patch here, and you simply make a difference between this patch here. And then you can compute the sum of absolute differences or sum of square differences of these two things here. I mean, there are actually a lot of advances. We just did this BMVC. We've got a quite nice paper coming up. I mean, you first of all can use bilateral filtering weights or other weighting weights which are more sensible than just using the whole square. Actually, we have there a paper which even looks at finding a 3D orientation using some new method called patch match, and it even on some of the approaches I show later with all of these propagation even outperforms some of that. So unary terms are actually quite powerful, and it's worth to look into getting best unary terms. Okay, so the pairwise terms here of that form, and I will explain that now. So one possible way of the pairwise terms is to say this is the difference in terms of a labeling of two neighboring pixels, so it's a 4 connected. If they are the same, you pay 0 cost, and the higher you go, the more the difference is, the higher cost you pay. And actually for this energy, and I will come to that later, this is like, because it's convex, you can actually get the global minimum, and this is for the image which I showed before. This is the global minimum of that image, and this is of another image, the minimum. But actually, if you zoom in, you see these effect that there's not a sharp boundary between let's say the lamp and this part here. So does somebody know why there's not a sharp boundary? Sorry? No? Yeah, that's right. Yeah. So if you think about it, it's cheaper. So if you have a big jump here, you would pay this high penalty. And it's actually cheaper to pay, I don't know, 3 times a smaller penalty than paying 1 big penalty. I mean, it depends on the cost function here. Sometimes people choose quadratic, for instance, and then it's even more. Well, thinking with a linear one, it might be that it's probably equivalent with the two. But if it's a quadratic function, it's most of the time it's higher. It's more to pay a big jump than a small jump. You rather do a lot of small jumps. So then that was the main idea behind, like, and Andrew Blake did that in '83, and it's very fundamental to actually to computer vision to have these kind of like robust potentials. You say, well, at a certain stage, I just don't want to pay a more higher penalty, higher and higher. You say pay a constant penalty. But just actually, just for interest, it's not true that for all of the functions you necessarily have this kind of truncation. I actually just let me skip back even to this to what we had here. So that was here the energy which we learned after for doing denoising, and it was really interesting. So what we learned here was actually this is exactly the same energy, but now for denoising instead of finding depth information, right? So it's the same as like the di dj is now xi xj, and it's kind of interesting because the w, which I didn't really explain at that time, I should have done, is really every possible difference of these pixels is a potential label, as a potential value, a w, and we learned that. So in this case we learned, there's 60 difference, so we had it symmetric. So we learned 60 possible values, and that was all done with this loss minimizing learning, and actually it really surprised us as well that it really came out as an L1 norm, more or less. So it really was a straight line, because a lot of people before, I mean, that was just very recent work I've done. Always people said that there should be some truncation, but surprisingly for the pairwise term, for this particular application, we didn't find any truncation really. So L1 is actually sometimes also a good norm. And funnily, I mean, for the unary term, there is actually a bit of truncation in here. But that's just as a side comment. I mean, truncation makes sense for a lot of applications, but when you really learn the energy, it might not always be that truncation is the right way to do it. Yes.
What does the decreasing part mean? I understand the
Yeah. So this one here, or?
Yeah.
So
Anyone.
Yeah, anyone. So it intuitively doesn't make much sense. The data said that, but the main thing to remember is you don't have much observations in this area. Basically, that means you choose a very extreme value which you rarely observe in training. So in training we observe the x, the z, and the x. And if you were to make a histogram where most of these differences happen, they're all in here. This is probably, I don't know, there are like in these millions of pixels, there are probably, I don't know, 100 or 200 which fall into this regime anyway. So it's very unstable, and it just happened that it learned that. But these ones are not, these tails are not affecting the end result much. If you choose it different, you would get the same result, probably. Was that clear, or? Okay, okay, so now let's look at some stereo matching, and this is really comes down to speed as well. If you just have a pixel independent winner takes all, you might get such a result. But as I actually said, we have this BMVC paper where we actually really did the best in terms of patches and 3D orientation of the patch, and actually get results which are state of the art for some of the images. So you can get with such things as well pretty good results. But this one here is a quite simple one where pixels is a quite simple technique to do it. Then when you have scan lines, that means you just have a chain, and when I come to the optimization, you will see that you can compute the global optimum for a chain. You get such results here, which are often streaky because obviously the scan lines are not connected. So you compute for a scan line the optimal labeling, right? So these ones are sensible smoothing, and you get clearly an improvement over this one here, but you don't have any connections in the horizontal direction. This is then a result with a full connected grid, and I come in 5 minutes to one which is even more better results, which is more sophisticated than this. And this is some ground truth. Some pure student had to actually hand label this image, right? And nowadays we have a lot of ground truth which I acquire from real setup on an optical table. You put some objects in and move them on an array. You move the cameras on a line, and you have a rig, and but that was still done with labeling of a poor student in Japan. Okay, so another application where full connected is very useful is for instance texture synthesis. So if you look at this example here of some text, this one here was created fully automatically from this one here. And actually, if you start to read it, I'm not sure if you sit close enough, but actually you start to read some of the text, it doesn't make any sense. But I mean, visually, it doesn't look that bad, right? So how is that done? So how it's done is we take this this text here, or this example image here, and we now think about in 3D as taking this one and laying this one here a shifted version on top. right? So we just simply make this one a bit wider in this direction. So we lay the 2 on top, and here this is the 2 on top. We have to find, we want to make this a big text, so we have to somewhere transition from this text to the other text, right? From this image to the other image. The question is, where do we transition? You can encode that as a binary problem, where there's a 0 for staying in this image and 1 for going to the other image, okay, from A to B. So where do we do that? We encode it as a binary problem of the following form. We look at 2 neighboring pixels, and we encode what is a good transition. So if it so happens that at I and at j, the 2 pixels at A and B have the same color, it's a good place to transition. Because if you just see this here, it doesn't matter what the labeling is, it always looks anyway the same. If it's 0, 0 or 0, 1, 1, 0, 1, 1, it's like whatever labeling it is, it always is the same image, right? So you can easily transition at such a place. Where it is in this case, it's very hard to you will see a transition. If you have here the same colors, but here's a different color, if you have 0, 0, 0, that means you stay in here, or you transition here, you would see it visible because there is a color transition, right, from going from 0 to 1. So we simply encode it in this following energy that we say at I and at j, we take the difference of these 2 pixels here, and there are no unary terms, it's just this pairwise term, and we pay this penalty here if there is a transition. If for a transition from 0 to 1, this is 1, otherwise it's 0, we pay this penalty. Okay? So this is how you get it, and this here is actually for, you can just do the same for volume for a video. Let me just play that. So this here is a short video, and now the idea is to make a long video, and you simply can do the same trick doing it in 3D. So you have got the short video as a video cube, right? And now you take the same video and just shift it by some amount in the temporal direction, and now you say find a 3D surface which labels, so every pixel has to be labeled 0 or 1, and where there's a 0, 1 transition, it's exactly the same cost as I said before. And now the nice thing is you can get a new video which is longer, and at every pixel here that might be at a different time a transition to the other video, right? And so try to find the best surface here. It's again, it's called, what was the name? Video texture, I think, video texture. And this is the approach, and this is then the end result. So it's quite hard to see any transition really, right? It plays on forever. No, it stops now. Okay, so the same actually can be used for panoramic stitching. So again, you've got here multiple images, and they're overlaid. You have already registered them with some interest point detection and some homography alignment. And now the goal is to find the labeling. In this case, it's no longer binary; it's multi-label, and then you get exactly the same energy. You can get this result out. Okay, so we've talked a lot about connected MRFs, and so there are a lot of useful systems have been built. And one of the possible reasons is when we look for the optimization part, it's a lot of good and globally optimum solvers which are globally optimal. Okay, let's move on with higher or 8 connected pairwise MRFs. So we've seen the knock-on effect in good systems, but what is missing? So we'll go through 4 possible applications where highly connected MRFs have been used. Modeling real-world textures, reducing discretization artifact, or that will be in stereo, encoding complex prior knowledge, or using non-local parameters. Okay, so this one here is more of a simpler toy one, just to illustrate the effect of using higher connectivity. So this one here is a certain set of training images. This one is a test image with a lot of noise on. This is the best result you can choose if you have a 4 connected pairwise MRF with some unaries. So the unary says if it's black, it's more likely black in the test image. If it's white, more likely white. And then you really try to learn. I haven't done proper learning here, but I think it's close to optimal. The weights of these pairwise term of 4 connected, this is what you get. So now if you choose other links, you say, well, why the 4 neighbors? You could also choose a bit 4 longer range ones. You get such a result here, which is already visually more pleasing. But if you get higher connectivity, and this is the best I could achieve, like this was a 9 connected, you get such a result here, which is better. Still, it's not pleasing. I will come when it comes to actually higher order MRFs. I will show much better result here. So interesting, these were 9 connections, where 7 of them were attractive, meaning you prefer the same labeling, and 2 were repulsive. You say, well, actually at that distance I prefer a different labeling. So that's quite something also quite important, discretization artifacts or metrication artifacts, which are discussed quite a lot, especially with variational methods, what Andrew Fitzgibbon will talk about. So here, let's assume this is part of a segmentation, like it goes here, and it either goes the blue line around, or it goes this yellow line. Obviously, so first of all, the yellow line has got a length of 5.65. And this is 8, where 1 is a unit square is 1 here. So obviously such a segmentation would be not possible, so we have to follow the pixel grid, right? So can somebody say with a 4 connected MRF, what would be the, which segmentation would be longer? This one here or the dark yellow one with a 4 connected MRF? Yeah, that's right. You're very quick. It's the same because if we count the links, it's like these one here, 1, 2, 3, 4, 5, 6, 7, 8, and it's 1, 2, 3, 4, 5, 6, 7, 8. So it's exactly the same thing. Independent of how we choose the weights, it's always like the same length. Now if you have 8 connected and more highly connected, you can actually show that you can really encode the true Euclidean length of the thing. And there is some nice work by Yuri Boykov and Vladimir Komogorov, and they have really shown that that you can get to the true Euclidean length. But to be honest, like for problems where you've got data observation, where you have some, I come to that in a second, there are problems to overcome this. But anyway, so let's first look at 4 connected. This is a result of segmentation with pure 4 connected, and you get these kind of called Manhattan artifacts, where there's some straight corners because we cannot distinguish between straight corner and a nicer segmentation. And this is 8 connected, and you kind of see a bit of rounding off here. But then, as I just hinted to, there is the, like, if we make it contrast sensitive, you anyway get much nicer results, and if it's 4 or 8 connected, it's fine. So it's like if it's as long as it's depending on the data, you actually you don't see these metrication or these artifacts really. That's different, and that's quite a lot of work people do in the variational domain when they talk about 3D reconstruction, where there's no underlying data really. So in the images, every pixel you've got an observation. In 3D reconstruction, you sometimes have some observations in here from data, but might be very sparse, or you might just only have a silhouette and you want to construct a full 3D volume. There you really need, even in a 26 connected grid, and it was done, work by Daniel Kramer's done, 26 connected grid, you still see some metrication artifacts quite horribly, but this is all if you don't have any data. And a lot of applications, Kinect and so on, you have got data and you rarely see these artifacts, I think. Okay, let's come to one encoding complex knowledge. So here again, this is called Tsukuba head, where we now want to get better results by thinking about occlusion. So in the real world, you can see sometimes objects moving behind other objects, they are occluded, and we haven't thought about that in our simple 4-connected problem. So here the idea is actually to label both images with these 1 to D with the labeling, so both images. Additionally to a standard 4-connected, we also have these long-range links linking every pixel here to all the pixels which are potential matches. Okay? And these links here have a very particular form. They are of the form here that that if I have this one pixel here and the other pixel here, these label this and you choose any potential labeling here. It's either infinite or 0 cost or a cost which I pay for a match when they really so it's called match cost when I have this unary cost which I pay. And this is a very, very particular structure, and explain now why such a structure arises from occlusion reasoning. So first of all, you might have the scenario that you see with the two left and right view, this is a top view, you see really the same object, like at a certain depth, let's say 10, if you have the same depth, then you pay this cost because it's on the same surface, you pay this matching cost. You can also have this blocking here, so there's an object in front of it, and if it blocks, then you don't pay any cost, and you would pay this matching cost for some other pixel here, which we really have that matching here, right? So that's fine, it's correct, zero cost. But what you cannot have is that one image sees this here, but the other one sees further away, because that would look through the object, right? And so this is an infinite cost. You cannot see through objects. So this is a very, very special structure, and it's a much more complex, highly connected MRF. And a bit later on, when I come to the comparison, we see that this is much harder to optimize than a standard 4-connected. And you see that now the results with occlusion reasoning are much nicer now. They've got this here is with occlusion reasoning, and versus this is without occlusion reasoning. Okay. Now let me come to like non-local parameters. So this was what I showed before with the brushstrokes here. There's actually, if you if you say that an object should have a certain color model, and the background might also have a compact color model. Before we got it from the brushstrokes, but we might want to get it directly from the objects. We should say all the foreground pixels have a color model, and all the background pixels have a color model. Let's try to find a segmentation so that these color models are as compact as possible. Like for instance, extreme one is just a red pixel is one distribution, and all of the others are another. Then all of the other pixels are pretty broad distribution, not very compact. And the compact distribution is preferred compared to wider one, which is automatically if you write down the probabilities. So right. So actually, that's something I've done now 7 years back, where you just draw a rectangle, and Andrew actually showed that. And let me give you a quick demo of it, how this works. So right. So I've got the image. It's a bit funny shape, right? Anyway, so you click here. This is the background removal tool in Office. So when you click here, you get a rectangle, which is at the default position, and so you have to move it into a bit more sensible position here. Here, okay. We can cut it and paste it here. And, right. Yeah. Right. So yeah, meeting with the Queen. Right, so what's the underlying theory here? And this is actually, there's a lot of approximation going on in the background because it has to be fast. But what's really underlying in the background is we have a color model, we have a global variable called W here, which is really exactly this Gaussian mixture model for foreground and background. And we try to optimize jointly these Gaussian mixture model for background and foreground, and they impact the whole segmentation. So we prefer, once we have this one here, it's actually getting unary term. If you think of this one being shaded, observed, then it's getting unary term. This is actually, later on I will explain how to optimize it, how it's optimized. But in general, it's a very hard optimization problem because you've got these highly connected MRF. And this was actually also used for an object recognition segmentation system. So that was Texon Boost we had a while back, where exactly there you have got, let's say, k different objects. It could be tree and grass and building and sky. Now you want to fully automatically segment that. You have these color models, which are exactly as I explained, so that all the white is more likely house and all the blue is more likely sky. You have a location term here. And the location term can be, for instance, that sky is more likely at the top and grass more likely at the bottom. This is a unary term. You have another class unary term, which comes from, you have to read the paper for the details, but some kind of boosting of features. So you have features which look at surrounding, at rectangles, and at a certain texton is like a certain, how textured it is, and it's boosting of these kind of classifiers. You could also use random forest or other classifiers here. So this is a unary term, and then there is a pairwise term which is also edge sensitive. And here's an example, for instance, for cow detection. So this is the image here with the cow. This is what the class and location gives you. So it roughly nails the cow. When you add edge sensitivity, you get a nicer segmentation. When you add color, it simply says, well, okay, all of the black should be cow, and then you get the nice segmentation. There are many systems these days which I don't want to go in detail, which have got such a structure where there are the observed variable z, there is a grid of pixels, for instance, which are latent variables, which could be called parts. For instance, this is from the layout CRF from Win and Schotten, where they have split like a car into different parts, and they learned random forest to say what each part might look like as a unary. And then they have connections to say that neighboring pixels should transition within the same parts, or might transition between, it's actually a directed field, might be neighboring part or up or down part. And so now there's an MRF or there's a connectivity on the parts. They have another layer where they say this is the instance label, so all of the parts go together, then form an instance, and you get a number of instances you can get out. And then they have got some global variables which really describe what is the orientation of the car, which way in 3D even could it be, which way is it facing, what's the size, and so on. As in Kinect, you can think about what's the height of a person, and so on. Is it like what's it female or male? You can have these kind of global variables up here. So these are quite complex models. A lot of people have done recently. Most of the people, because we talked a bit about marginalization before, maximize over all the variables. So when we compute map, we maximize over all of these variables. But you could also think about marginalizing out some of them. You could say you really want to marginalize out with respect to all of the variable t. But typically people do maximization, and that's still feasible. I mean, it's still possible to such networks. Okay, so we talked about highly connected, now higher order random fields where there's really a factor which talks to all of the variables. So in general, I mean, the higher order factors cannot be, in general, and there are special cases obviously, cannot be decomposed into pairwise. So there are several reasons for using higher order, and I will explain only some of them quite briefly. So that is, we get even better images or texture model. There's like a field of expert or curvature we can model. Then we can have global priors which really act on the whole image, like connectivity or better encoding label statistics, or converting global variables to global factors, which is also quite interesting. So let's just look briefly at some of them. I had these texture images before where I think this was the best result with a 9 connected. So recent work we've done, and you should have to read the paper to get the details, but the idea is that we have higher order potentials of that size here. So these are patches of the size, I don't know, 9 by 9. And what you simply say is that these factors, you prefer to choose them, but you don't have to choose them. So there's a factor which says that either take these 3, or they're in total, I think, 20 or so, take these 20, or take an arbitrary labeling with a higher cost. So these ones have got a low cost, or you take an arbitrary higher labeling with a higher cost. And then you get such results here, which is kind of, it's pasting together these patches here, but it's using them in a soft way. So you don't have to use these patches. If you were to rigorously use them, I have the image, but I forgot to put it in here. If you're really forced to use it, you will not get such a nice result. You really have to use it at some place in a soft way. So this is an example of a higher order random field. But I mean, I have to say the optimization gets harder and harder when you come to higher order random fields. So this one here is a global prior. We've done some work on connectivity. For instance, the user has scribbled here and scribbled here as well, and now he's got this segmentation, and now he says, well, I really want to have these parts here and this part connected. So I want to have a segmentation which is connected. Then we can get such a result out by just saying it has to be connected. You get a really nice result, which would be very, very hard with doing these brushes and really segmenting it completely. And it's very simple to write it, but then it's obviously complex to optimize. But I will explain how it can be done. And it's very simple to say, well, it's infinite penalty if it's not for connected, the segmentation, and otherwise, if it's for connected, it's no penalty. Okay, so this one is a recent work we've done on global prior on the label statistics. As I said before, is the most trivial labeling, which is all black or white, is still more likely than this here, and that can still influence the results. So here's again like denoising, where this is the task here, the ground truth, and this is the noisy. These are results with such a truncated linear function, and we've increased the weight of that pairwise term, and it's getting more blocky. And this is the intermediate results we get, sometimes less blocky and sometimes more blocky, depends what you want to have. But it's now interesting to look at the statistics. So this is a statistic of gradient. So here we take all of the pairwise and look at what is there, how often does it occur? And that goes back to your question before, where you said, why actually was it like the other way around, the potential? Because there are not so many, but still there are some occurrences of these gradients which are with high values. But probably before we looked at this range where it really never occurs. But still, this is the distribution of the gradients, and we look at these results here, and you look at the gradient statistics. They are far away from the statistics, right? There might be the peak of this here might be similar to this one, but then the distribution goes down and makes this dip here, which is not natural. And then if you try to push that up here with such a result, it's getting more like this shape here, but it's just completely wrong. It's far too peaked here, right? And so what we've done here is, like, for instance, you could have a global factor which simply says, well, what I want to have is a result which follows that distribution. So what we've done here is a work which is mainly on the optimization side. We show that it's possible actually. There is, I think, a black line here which is the result of this image, the statistics, and or the red line, and it follows much more this line here compared to the best one of this one. So it's really forcing this statistic. Okay, so these are all useful models. How do we optimize them? And this will be the second part. I think I've got 15 more.
35 minutes.
Pardon?
35 minutes.
35. Yeah, that's right. Yeah. Okay. So before we go into that, let's have. So this here is like an example of a quite advanced conditional random field we've done for a SIGGRAPH paper. So it's called the unwrapped mosaic. So here, this is a person talking, and what we solved is we've solved a lot of problems, but it's using a lot of conditional random fields underlying. So you see here the moustache appearing. Oh, stop. Right. So you see the moustache appearing and disappearing, right? So you'll see in a second how it's done. So what we've done here and this here is we use the head and we kind of unwrap it as one surface. So we're trying to have this ear being on this side, and hopefully when the video continues, I don't know what's happening. Right. So this is the whole unwrapping of the face. And once you have that, you just have one image where you can do painting on. What's happening here? We can paint on moustache and eyebrows. And then we've got the full registration of this image here, where it would link back in the video. And this is just to highlight the edits. So there's a full registration of the video with this mosaic, and it solves a lot of optic flow and embedding of the surface into the video, and it's a lot of different energies to optimize. Okay, so before we come to optimization, let's make a small detour to continuous variables and continuous domain. So Gaussian MRFs or continuous valued MRFs are quite popular, though actually not so many people have worked with these models, and I think actually it deserves a bit more attention because they might be quite powerful. So here is an energy with where it's again a unary and pairwise term, where now the xi is a continuous variable r. Okay, and so here, for instance, we have potentials where the pairwise term and the unary term and the pairwise terms are of a Gaussian form. Or in general, if they're of any convex form, you can get, during optimization, the global optimum. And typically for optimization, people use gradient descent or some other schemes, and I will not discuss any of that. But it's quite interesting. With the continuous models, either people stay with Gaussians, a lot of people stay with Gaussians. If you go outside Gaussian, everything gets much, much harder. But with Gaussians, actually, it is everything is tractable, learning, and also the inference because of convex. There's only one global minimum. So here's a result which is not so impressive. So it's like in painting, and if you just use these energies, the result doesn't look that great. But it's just to show that if you were to use discrete labels with 255 with TRWS technique, which I'll come to later, you get this result. And if you use just a continuous solver, it's called hierarchical basis function. It's like it gets the same result as to be expected. It's the same minimum, but it's like 15 times faster. So one message is to take, if you have energies which are of a form of Gaussian, then it's actually there are much faster solvers here available and give you good results. There is like one interesting work called the field of experts, which is a higher order random field, and it's of continuous variables, and this is no longer convex, and they had really quite hard time during both learning and optimization. So this is I don't want to go too much detail, but this is like here, this x is the labeling here. You do convolve with a filter here, J, and these are possible filters, and these were learned during the learning procedure. These filters are learned, the weights of these filters are learned. And these are linear filters, linearly combined with this one here. Now it goes through a non-convex function here with some weights. And then you basically sum over at every position here, every pixel you've got such a patch. So it's a sum of all of these, so all of the filters here, first of all, and then at all of the pixel positions you've got one of these filters. So it's a very highly overlapping filters which are then due to this function here non-convex, but they get much better results than the standard smoothing which I've just shown. Like for instance here they've done this image where they put some text on what you want to in-paint. They use gradient descent during during optimization. So this is the field of expert result which really nicely paints that in here, where this is the result with just a smoothing MRF. So you clearly see this is a pretty much better result. So this was here quite important work on the field of experts to show that higher order random fields are useful, and they've done a nice comparison between 3x3 filters, 5x5, 8x8, and so on. Well, actually they stopped with 8x8. 8x8 actually not performing much better than I think 7x7 would not perform much better. 9x9 would not perform much better than 7x7. So, so just this is a hint, and Andrew Fitzgibbon will go in a lot of detail about continuous domain methods. So what's continuous domain? And there's actually a very nice paper which I encourage to read by Stefan Rother at the CVPR, which connects discrete domain models or objective functions with continuous domain ones, right? So, so in continuous domain, let's assume this is the input image. This is just like very zoomed in on the pixels. So these are the individual pixels here. You think about this whole area here as a continuous function. So one way to, for instance, model this function is using finite elements, and one of the most simple things is to say, well, let's first use a triangulation as the underlying basis. So, but they have, in this work, they have done it with a lot of different variations of this one here. But, so for instance, you could think about, at all of these points here where the triangles meet, you have, at all of these vertices, as the blue ones here, you have an arbitrary continuous label. And in this way, you can think about all of these triangles being slanted surfaces in kind of 3D. And this gives you a continuous domain function out. So you can choose all of these blue pixels, you can choose a different continuous value. So this gives you certain families of continuous functions. And then what they have shown is actually if you have this standard called total variation term, where there's some convex data term, for instance, which comes from the unary, convolved with this image, also sometimes in discrete, sometimes continuous. They have done it also this one, the data term continuous. And then this total variation is very similar to the standard pairwise smoothness term which we had. So it simply says the first derivative you want to penalize, and it's just a linear norm on the first derivative, the total variation. Then you can actually show that you can write exactly this thing here if you have this basis function as a triple clique MRF, for instance. So this is, you've got all these nodes here which take some continuous variables, and these ones here are triple cliques, and this here does exactly the same thing as this here. And they've looked at a lot of different ways of how to write this with different finite elements, and how to write the discrete one, and then compared solvers and looked like what are the pros and cons. And just for me, a bit of the summary with this discrete continuous is the advantage of the continuous are that it's independent of the pixel grid. That's the whole idea. They kind of, people say that the world is continuous. Why should I start to use pixels as my labeling? And they're very fast for these quite simple energies. They're very fast GPU solvers, which do convex relaxation and very fastly solve it. So that's the positive things. I think some of the disadvantages are that if one talks about the continuous world, one really has to think about camera point spread function, other effects, because otherwise there's a lot happening until you get to the pixel grid. And if you talk about continuous world, you also have to model these things, which is rarely done now, or rarely seen with these continuous approaches. They can so far, now there's interpretation with discrete models, but so far there's no probabilistic explanation, there's no learning involved yet in these continuous domain models. And also the variational models are rather simple in the sense they take first or second order derivatives, but like in that work they compared to the field of expert result, which is just like a highly connected grid, which would be, I don't know what it means in the continuous domain, but would be quite different, might be a very highly connected whatever in the continuous domain, hard to say what it is, but it outperforms the continuous methods. So I think there it's like, if you go to the level of really trying to model a point spread function, really trying to model the world, it's worth to think about continuous domain methods. But otherwise, I think the discrete is fine. Apart from these, they have got pretty good solvers for some of the, where it's only one, where there's a global minimum convex problems. They have very fast solvers, which might also be interesting to look for this in the discrete domain. Okay, so any question to the part I've shown? Otherwise, I step into optimization techniques. Right? Good. All right, that's a question, sorry. No, far away from real time. I think it takes several hours to compute the full registration, everything. Once you have the registration, it's real time, obviously the editing, right? Because you have the whole mapping of the surface, of the unwrapped surface to the video, and then you just can paint on it, and in real time you can play it back and edit it, right? But this registration is a very complex thing, and there are also sometimes user interactions needed to really get it a good. I don't know exactly. I was not in. Pushmit Kohli mainly did that, and I think they read several hours to get a good registration. Yeah. Okay, optimization techniques. Let me start by motivate why optimization or good optimization is important. So here is an example from an image sequence where you want to compute an intermediate frame. So you might have a video camera which moves like a bit down, and you see, or like it moves up and the object moves down, and now you want to compute an intermediate frame. And for this one there is one approach which Fritz Given and others have done, where they convert that into a pairwise Markov random field, which actually is a binary. With each pixel, you know there's one or the other color, and you just have to decide which color you want. And they use some patch space MRF to get some patch space method to get to that, to get MRF. And so so actually Oli Woodford, a student of Fritz Given, asked me to optimize that, and was quite interesting to look into into some of the results. So let's zoom into this area here. So this is the ground truth. And this is the results with different methods, and they're all not globally optimal. And so this is GraphCut, and I will come later to it. But it's this was an energy which cannot be optimized with GraphCut. So we had there was some truncation needed, and so there's an approximation. And you see here, this is not nice that it got this here and this here. Belief propagation get this result, and I will explain what belief propagation is. But you see here, this part here is missing out down here, and that was slightly better, I think, in here. And this is simulated annealing, yet another technique. So now we looked at it, and that was done with Viktor Lempitsky and others. We looked at extension of a certain techniques we called QBBOP, and it just happened that for this one, I mean, for other parts of the image, it might be very similar, these techniques. But if you looked on this part here, it happens to be that we get the global optimum, and we suddenly see the result looked actually much nicer. And this is really very often when you start to develop very fancy models. You run some optimization, then you say, well, it doesn't really work. So what do you work on? Do you work on the model or the optimization? And it's just, always you have to keep that in mind, that it's quite good to look at alternative optimization techniques. There are, for instance, very simple ones, such as simulated annealing, which are not very expensive to run and to test, and it's always worth to test that, because we've sometimes actually been surprised. I will show later results where we run simulated annealing, and actually they got extremely good results, which you wouldn't expect beforehand, because there have been a lot of papers in the last 10 years to say, well, we really worked hard on these kind of combinatorial optimization methods. So it's just worth to look around at different optimizations and to spend a bit time to see that before you jump into improving your model. Obviously, you see now it's also good if you get this global optimum, you know at least the global optimum doesn't have some of the highlights here. I mean, probably it's a bit hard to see because the sun comes in, but there are some highlights here, like this here, which is not here. It's smoothed out. So you might want to represent some more highlights to get a visually more appealing result. Okay, so recap. This is how we write our energy for the optimization part. So there are some unary terms. There are some pairwise terms here. This is a sum over sum of the pixels xi. These are the pairwise terms, and there might be some high order terms here, which depends then on multiple variables. Okay, and the label space can be either a binary label space 0, 1 or multi-label 0 to k. Okay, so this is the big picture, and I've got another slide with all the possible inference methods, and I will try to cover quite a lot to give you the flavor of all of these methods, what's going on in the background. I will go into very detail of some of them. I explained GraphCut, for instance, in detail, but for some of them I only a bit scratch on the surface that you get an idea what they're doing. So there are combinatorial optimization methods, and that will be the main part. What I talk about, there are so-called dual or problem decomposition techniques. There are local search techniques or genetic algorithms. There are message passing algorithms, and I will go into some more details here as well, and some of the details of LP relaxation techniques. Yeah, so these are the kind of 5 different categories of methods. These are all for discrete labelings. And that's just on the big picture. If you have like these higher order potentials, they're tractable up to a certain size, like up to order of probably 6. It's possible to actually, for arbitrary potentials, to optimize them, and there are either message passing techniques or combinatorial optimization techniques, but they get just very both a certain size. If they are arbitrary potentials, it's just very, very hard to optimize memory and computation time. Above this kind of like 6 or 7, it's still, there are quite a lot of interesting potentials, but they all have certain special structure, and we'll come to that then. What structure is good to, which are still tractable to do inference. Okay, so function minimization is that's a very big part of, like, I mean, optimization community. Two very important questions are which functions are exactly solvable, and approximate solution of NP-hard problems. And you just, I mean, I just list here some of the researchers from the vision community which have worked on these problems, and there are a lot of papers appearing on discrete optimization. Although I think on other domains, like as I said, continuous labelings could also, there could be even also some more work, but people concentrated in recent years quite a lot on these discrete problems. Okay, let's start with one particular one, which is message passing, and I will explain the following method, which is dynamic programming or message passing on a chain, and then I will go on to trees, and then we can see how loopy graphs are done, or graphs with loops in them. Just give me a short break. So, so let's assume we have the following energy where there is we've got only 3 nodes, P, Q, and R, and we have some unaries on the P label on XP, and can actually have 3 labels you see in a second, and there are 3 different unaries. There could be, I don't have that I think here, for Q and R it could also be unaries, and then you've got pairwise terms for these P and Q and R, and they are of the form, if they are the same, we don't pay anything, but if they're different, we pay a cost of 2. Okay, so the question is now for this chain here, and I will show here these are the unary terms. So if it's P's in state, there are 3 states, 1, 2, and 3, let's say, the unary costs are 5, 1, and 2. So the question, how can you write an efficient algorithm to find the global optimal labeling of that? So you want each of these pixels got 3 possible labels. We've got this energy here with the unary term, and you might have some unary terms here as well, and pairwise terms. How can we find efficiently the global optimal? And this is called dynamic programming, and it's very simple. So we compute so-called messages. A message is the information which is passed on up to node Q, and encodes all of the things we have up to node Q, all of the unary and pairwise terms. So what we do is we has a message has got 3 values, and we say the first value says what is for this pixel Q, if it were to be in state L1, the first state, what would be the optimal configuration for these ones here? So we say, okay, if it's this L1 and it were to be this one here, P would have been also in state L1, what is the cost? We have a 5 plus 0, because the pairwise cost here is 0, it has the same label, so 5 plus 0. Okay, now it could be in this state here, which is 1. So we've got a unary cost of 1 and a pairwise of 2, because it's different. Okay, so it's 1 plus 2. And this here is 2, and it's also different, so it's 2 plus 2. Okay, so we take the minimum of these, which is in this case it's 3. It's the middle one. So we mark that link here as being the optimal one, as the optimal link, and we also know it's the labeling of this is 3. Okay, so now we can go do the same thing for L2 and L3, and this is then the message which we compute up to node Q, encodes everything. So we have got 3, 1, 2 as the labeling here. And just to confirm, the 1 is from this link here, which is yes. So this is the unary 1, and we pay 0 cost. And this is a 2 here, and we pay 0 cost. Okay. So this is the message up to label up to Q. Okay. So now we compute the message up to node R. And how we do that is we take all of the information in here. So we have the information up to here, and now we encode that information coming in here, the message coming in here, the node Q, the unary here, and the pairwise term here as well. We take all of that together and compute, and that computes the new message up to node R. Okay, so assume here we go again through all of these labels here, and now it would be such a connection here. So if I take this one here, I would go here. If I take this one, I would go here. If I take this one, I would take this as the optimum one. And now we can simply read out the optimum because we have got the message up to here. We've got also the unary at this place here. So we've got F is the unary at this place. The message up from Q to R, exactly, from up to here. And just take the minimum of these two, and this gives us, and it might be this label here, gives us the global minimum, first of all, in terms of value. And then we can trace that back the path, and we know this is the optimal one, so we just trace it back here. So this is the path, and this is the global optimum of the whole thing. And it's just, you think about it, we just carried on all of the unary and pairwise terms in a sensible way, computed all the messages. So we can have a forward pass and a backward pass, and then this gives us the global optimum. You can actually state instead of this is now the global optimal solution. You can also take marginals. Then you have instead of taking max here or min here, you take a sum, and that's called then later on when it's BP. It's like instead of there's max product BP and sum product BP, which sometimes some product BP does the marginals and the other one does the map solution or the global optimum. So we see here this is optimal for a chain. So it's global optimum in linear time. So now for a tree. We can start with a leaf leaf P here, Q and R, and this is another leaf S, and this is the root. We can get again with dynamic programming, we get the global optimum. So we've got an inward and outward pass. So in the inward pass, we first compute a message from P to Q, then from Q to R, which in this case I indicate takes all of the information up to this point here. There's another message from S to R. And now there is a big message which takes the incoming message here, the incoming message here, the unary term, and this pairwise term, and then computes the new message. And that's up to this node here. Now with this message here, with this message here and the unary, we can compute the optimum, and then we can trace it back as we've done before with the links, and this gives you for a tree the optimal solution. Okay. Now, so now people have thought, okay, it works on trees. What shall we do if we have loops in the graph? And people just said, well, let's just apply the same algorithm really and just update these messages until certain number of iterations. And there's a lot of theory behind different update schemes, and I'm not an expert on these kind of things. I don't want to go into so many details, but but there are different schedules. There's a sequential schedule and a parallel schedule. It's about how do you initialize these messages. But again, there are just like you look at the incoming messages at the node here, at the pairwise term, you compute the outgoing message. And then you can do this message, and then you can do this one, this one, this one. You can do it sequential fashion, or you do parallel all the messages. And there are different, there's quite a lot of theory around that as well, what works better than other things. One important speed-up trick for these message passing is if you have certain potentials, like if you have a POTS model for the pairwise term, or we had before a truncated linear. So remember these pairwise term, where it's like a form like this here. Then you can compute these messages in linear time compared to quadratic. So before, what I explained was I had to go through, in order to compute the message, I had to go for all of these nodes here. And for each one, I have to take the minimum with respect to this one. And this is a technique which automatically, there is some convolution with going on, and they managed to get it in K, where you just have to go linearly through one of these labels to get automatically the optimal message out without going through all of these ones. And that's a quite nice technical contribution, which also is very important for speed. If you use these packages, like Vladimir Komogrov has done a very nice package of different variation of these message passing. There you, if you have certain potentials, then you can, it's automatically doing the messages in a faster way, which is important.
Excuse me, is this something common with the generalized distance transform?
Yeah, exactly. That's a generalized distance transform. Yeah. Yeah. So then TRW is also another variant of message passing, and I will explain it in a bit more detail later when we come to problem decomposition. But so it's called a tree reweighted message passing. So it's it goes in the following way. You have your graph here and you split it into trees. And now the trees can be done, so the whole idea is like the main question is how do you split it into trees? And I will explain that in a later section. How do you then optimally, well, the trees are always fixed, like what exactly structure of the trees you choose, but what are exactly the variables here you choose for the unary and pairwise terms, that has to be determined, and we'll come a bit later to that. But you can think about these, for instance, unary terms could be split evenly up into these trees. So if this is like a certain unary factor, could be half of it here and half of it here, and there's a pairwise factor could half of here and or like half here and half here. And now what you do is you have you find the global optimum on the tree, and we explained how to do that. When we find the global optimum, there's something called node averaging, where you take all of the solutions of these individual trees, you average them, and get a new solution. And then with this new solution, you actually again invoke a new problem here, a new splitting problem, and then you optimize again the trees. And this will come a bit clearer when I come to the problem decomposition of one way of doing this here, this splitting, which is actually the optimal way of doing it. And this one here, there are various ways of how to do this, do these unary and pairwise terms, and these are then variants of this kind of TRW, tree reweighted message passing. It also provides you a bound, and I will come to that later when it comes to problem decomposition, why it provides a bound. And is also related to LP relaxation, which I will not go into much detail why this is actually related to LP relaxation. It's like it performs some reparameterization, which is then you can see as solving some underlying LP problem. So to summarize, so message passing, it's exact on trees. Or like chains, you might have some like model here where there is like a person model, or for faces and so on. And this is actually, this is also quite similar. What you can think about as being used in Kinect, right? You might have some observation here, and you then try to find the optimal layout of the body parts, right? And this is simply using a dynamic programming because it's a tree in the end. So for loopy graphs, there are many different techniques: BP, TRW, dual decomposition, and diffusion, and they're different in terms of the update rules. And you can either compute map or marginals if you do if you do the minimum or the sum when you do this, when you compute the messages. And there are some connections with LP relaxation. And there's also a variant for that for higher order random fields, where you actually have messages which go from nodes to factors and back from factors to node, and this is called factor graph BP, and it's quite it's not very often used actually in computer vision, but in machine learning people have used that. So for the details here, there are some recent tutorials we have done which go into these some of these details. Okay, so now that will be then I think the second lecture on combinatorial optimization. I mean, I can start a bit with it, let's say the first 5 minutes, and then we probably should stop. So I will talk about various different problems. So there's binary pairwise, multi-label and pairwise, and binary in higher order. And and different different techniques, either transformation techniques or move-making techniques. You just have to see, right. I might, I go briefly and I might repeat it in the next lecture again. Okay, so if you look at binary functions, one important question is which binary function can be solved exactly. And there's a so-called submodularity condition, which decides if a function can be optimized globally or not. And this is the condition of the submodularity condition. So, so for instance, if we have only two pixels or two nodes with binary labels, then we look at all of the sets A and B of which comprises of two variables. So it can be 0, 0, 1, 0, 0, 1, or 1, 1, and you have to plug it in here, the sets A and B, and has always to be greater equal than if you do the OR at the end operation on these sets. So for instance, a lot of these conditions actually, if you plug it in, they are like trivially satisfied. For instance, if we plug in, I don't know, we plug in, let's say we plug in 0, 0 and 0, 1, for instance. So A is 0, 0 and B is 0, 1. Then if you plug that in here, it would be 0, 0 plus 0, 1, greater equal to the OR operation is 0, 0 and 0, 1 is 0, 1, and the end operation is 0, 0. So you have got 0, 0, 0, 1, and here is 0, 1, 0, 0. So it's like, it's equal because they cancel out. So a lot of these, for all of these sets, it's all trivially satisfied, apart from the fact when you have got this condition here, which is 1, 0 and 0, 1, has to be greater equal 1, 1 and 0, 0. So this is a very important condition, and if this is satisfied, and we come to that in a second, it's very often satisfied for a lot of vision problems. If this is satisfied, then we can use a technique which I explain in detail called graph cut, where you get the global optimum out for this. So very nice important property is that, so I talked about two nodes here. That the sum, so first of all, we can also look just at one node, which is 0, 1, and this condition is trivially satisfied. If you have 0 and 1, let's say 0, 0, it would be obviously 0, 0, and this is all 0, 0, but for 0, 1, 0 and 1, it's, the OR is 1 and the end is 0, so it's again satisfied. So unaries are automatically satisfied. Now the important property is that if you add up submodular functions, they are again submodular. So if you have pairwise terms which are satisfied this year, all of the sum of the pairwise terms and of unary terms are also unary terms always satisfied, they're again submodular. So for image segmentation, we had kind of such an energy here where we had some unary terms, and we can also write 1 minus x, but this was always the pairwise term. It was always a difference and an absolute value of the difference of two. And so if we see here, if we plug in 0, 1 and 1, 0, this is here 1. So if you had 1 and 1, it's 2, greater equal, and this is, if it's the same as 0, so greater equal 0. So it's like, as long as the D is positive, this is always satisfied, the submodularity condition. And since here is a sum over all these submodular condition, the submodular terms here, it's also submodular, the energy. And we will see in a second, or in the next lecture, that this function can be globally optimized with graph cut, with using certain, converting to a network flow problem, and then this can be solved globally optimal. Okay, let's probably stop here. Are there any questions? Yes.
The submodular functions with the Hello potential still be optimized exactly. The submodular functions, but with Hello terms.
Yeah. So typically, you convert them to pairwise, and with auxiliary variables. That's you have to convert them to pairwise, and
it's always possible.
Yes, it's always possible with exponential number of nodes. I will in the next lecture, I've got some slides on that. So you can do the conversion conversion, and then you have to be, you have to be lucky to be a submodeler or not. And we will see some examples. All right, then that's it. There are no more questions. I mean, you can come to me if you have any more questions. Okay.